In this video, we're going to talk about the final step, which is getting the moment generating function of x bar when n is large enough. So to describe these conditions, we can say that we can get, like, when n is large enough, we can suppose a kind of radical situation that n is almost, n goes to infinite, and we can meet the condition that n is large enough, right? Because there's no more than infinite that we can do. And we get a moment generating function of x bar here, like this. So we get this result and compare with the result of normal distribution. The moment generating function of normal distribution, which looked like something like this. Oops. Yeah, something like this. We don't know this yet. So I try to prove this with this equation, not equation, with this form, from this form, but I faced one problem that we don't get this kind of form if we work on this form. So let me explain why. It's mainly because because we put n into infinite, so it actually ruined the distribution of x bar. So it's easier to it's easy to explain with actually seeing the distribution of x bar. So let's write down x bar and its distribution. And it's known that if we suppose central limit theorem already, it follows the mean of population mean and standard deviation divided by root n, which is the number of sample size. So we know this. So when we draw this here, like this, it look like this, and this would be mu, which is the population mean. But we know that standard error, which is the standard deviation of sample mean, it includes n here in the denominator. So what happens when we put n as infinite, that it goes up, and let me explain here. This part getting bigger and bigger, and it makes the whole part, which is the standard deviation of sample mean, like getting smaller and smaller. So in theoretically, it'll go zero because the denominator will go infinite. So what happens here is not distribution anymore, and it's getting smaller. The standard deviation of this distribution, smaller and smaller and smaller, like this, and finally when it goes n, it just converges to just a point, which is mu. So it doesn't have it's distribution technically, but it doesn't have standard deviation. So all the data would be just mu. So it's hard for us to see the distribution of sample mean. So that was the problem that I faced. So I decided to use a technique that we can actually ignore, square root n, getting bigger by scaling. So let's take a look what it actually means. So the moment generating function that we got, which was this, was the result of just a normal distribution. And I just said that my idea was scaling it so that we can actually get rid of the effect of square root of n in our calculation process. So which means is that if we know that it follows mean of mu and standard deviation as standard error like this. So if we suppose it is like s, and we get the moment generating function of s, then it should be, because we scaled it, it should be the same as result of the moment generating function of standard normal distribution. So to make the standard normal distribution moment generating function, we know that it's just the mean of 0 and standard deviation of 1. So we already got the result of the moment generating function of normal distribution. So we can easily get by put mu 0 to mu and standard deviation 1. So it would be just 2 here, and this 2 goes 0, and it's going to be 1. So it would be like this. So if we calculate the MGF of S here and compare its result with the MGF of the standard normal distribution, then we can still get to the result, get to the conclusion that central limit theorem worked. Because just by scaling, it doesn't guarantee it follows standard normal distribution. It's just scaled, nothing more than that. But if we can prove that it follows standard normal distribution, we can conclude that the previous value, the original value, which is sample mean, follows normal distribution. So this is the basic idea. So what we're going to do from the next video is getting MGF of S, which is scaled value of sample mean, instead of just get the MGF of sample mean itself. So yeah, this is the process, and see you guys in the next video.